Welcome back to the Deep Dive. Today we're unpacking something that I think often gets mistaken for magic, but is really just rigorous math.
Wrapped in a bit of philosophy.
Exactly. We're talking about the fundamentals of machine learning, specifically learning from examples. And I want to get away from the sci-fi stuff, the sentient robots. Let's look at this like agent design. How do you get a system to improve itself just by looking at data?
That is the core question of modern AI, and honestly, it's a question of necessity. People assume we build learning machines because it's cool.
Right.
But the reality is we do it because traditional programming just hits a wall.
The hard coding wall. Yeah.
Ugh.
I mean, if you think about it, trying to write code for every single possible scenario an agent could face is just a fool's errand.
Yeah.
You can't.
You can't. And the literature points to three big reasons why. First is just anticipation. So imagine coding a robot to navigate a maze.
Okay.
If you hard code the path turn left here, go straight, that robot is completely useless the second you put it in a new building. It has zero adaptability.
It's brittle. And then there's the problem of time, right? The world isn't static. If I write a program to trade stocks based on how the market worked in 2010 and I run it today, I'm going to lose all my money. The rules change. The agent has to change with them.
And that third bottleneck is the one I find most fascinating because it's a real check on our own ego. It's unknown solutions.
What do you mean?
Well, there are tasks we humans do effortlessly, like recognizing a face, but we have no idea how we do it.
Right. I can't write a function like an if-then statement that defines my mother's face in terms of pixel values.
Nobody can. So instead of trying to write a rule book we don't even understand ourselves, we just feed the machine the data, the experiences, and make it figure out the rules on its own.
And that's our mission today. We're focusing on one specific flavor of this, supervised learning, which is basically just function approximation.
Right. Finding a function that maps inputs to outputs. But before we dive in, it helps to see where it fits. You've got unsupervised learning,
Which is all about finding patterns in unlabeled data. Clustering. Like a taxi agent just noticing that, hey, traffic gets really bad around 8 a.m. and 5 p.m. No one told it that's rush hour.
it just sees the structure. Precisely. Then you've got reinforcement learning. Here, the feedback is really sparse.
The agent gets a reward or punishment way down the line.
Yeah.
A tip, winning a chess game, or crashing.
Yeah, and it has to solve the credit assignment problem. Which of the 100 moves I made 10 minutes ago actually caused me to lose this game?
Which sounds brutal. But supervised learning, our topic, is the teacher model.
The agent gets an input, it makes a guess, and the teacher immediately says, nope, that was a stop sign, or yes, that was a cat. You get these perfect input-output pairs to learn from.
And maybe the most intuitive way to see this in action is with decision trees.
I love decision trees because they're not a black box. You can actually print one out and follow the logic.
The classic example from the textbooks is the restaurant problem. The agent needs to decide one thing. Will I wait for this table? Yes or no?
It's a simple binary classification, and it looks at a bunch of attributes. Is there a bar? Is it a Friday night? Are we hungry? How many people are already inside, patrons?
So the machine builds this slow chart. But the real aha moment isn't the tree itself, it's how the machine decides which question to ask first.
Right. It could ask, is it raining? But if rain has nothing to do with waiting for a table, that's a total waste of a question.
So it needs a way to measure how good a question is.
Exactly. And for that, we use a concept called information gain, which comes from entropy.
Which is just a measure of uncertainty or randomness in the data.
Perfect. If I have a bucket of examples and half say wait and half say don't wait, my entropy is at its maximum. I have total uncertainty. I want to ask a question that splits that bucket into two new buckets that are as pure as possible.
You want to get all the yes answers in one bucket and all the no answers in the other as fast as you can.
And in the restaurant data, asking how many patrons are there turns out to be the best question. It has the highest information gain.
Why that one?
Because if the answer is none, the data shows we never wait. Boom, that branch of the tree is finished. Zero uncertainty.
Got it.
If the answer is some, we always wait. Done again. Now, if it's full, there's still some uncertainty, so we have to ask another question. But we've already made huge progress.
This feels a lot like Occam's razor, doesn't it? We're hunting for the simplest possible explanation, the smallest tree that fits the data.
We are, but that desire to fit the data perfectly, that leads us straight into the biggest, most common trap in all of machine learning.
Overfitting.
The memorization trap.
Yeah.
Imagine I give the agent a data set of dice rolls. And just by pure random chance, in this specific data, every time we rolled a blue die, it came up a 6.
Okay.
A naive decision tree algorithm might create a rule. If color is blue, then the result is always 6.
It's finding a pattern in random noise. So it gets a 100% score on that training data, but the moment you take it out into the real world, that rule is completely useless.
Completely. As the tree gets deeper and deeper, it's not learning a general trend anymore. It's just memorizing every single data point it was shown.
So how do we stop the student from just memorizing the textbook?
We split the data. This is the golden rule. You create a training set, which the agent can study, and a test set, which it never, ever gets to see during training.
It's the final exam.
Exactly. And if your model gets 99% on the training data, but only 50% on the test data, you know you've overfitted.
You know it hasn't generalized at all.
Right. And another thing we can do is pruning. We let the tree grow big and complex, and then we go back with a statistical tool, like a Chase-squared test, and check each branch.
To see if it's actually meaningful.
Yeah, to see if it's providing real information or if it's just modeling noise. If a branch is irrelevant, you just chop it off.
Yeah.
You sacrifice a tiny bit of training accuracy for much better real-world performance.
Okay, so decision trees are great for these categorical things. Yes, no, burger tie. But a lot of the world isn't clean boxes. Sometimes you need a smooth line. If I'm predicting a house price, I don't want a flow chart. I want a number.
And this brings us to linear regression and linear classifiers. We're moving from asking questions to fitting a weighted line to data points.
And the algorithm for finding that best fit line is, I think, really cool. Gradient descent. The best analogy I've heard is the blindfolded hiker.
It's a perfect analogy. Imagine you're dropped onto a hilly landscape in the middle of the night. You can't see anything. Your goal is to get to the lowest point, the bottom of the valley.
Because that valley floor represents the minimum possible error for your model.
Exactly. So you can't see the destination, but you can feel the slope of the ground right where you're standing.
So you feel which way is downhill.
Right. You calculate the gradient, the slope, at your exact position, and you just take a small step in the opposite direction of the gradient. You take a step downhill.
And you just keep doing that, step by step by step.
Until the ground flattens out. When the slope is 0, you know you've found the bottom. You've found the best fit line.
But linear models have a huge Achilles heel. They are, linear.
Right. They can only draw straight lines. And this became a massive problem in the history of AI with the perceptron. It's a simple linear classifier, but it famously couldn't solve the XOR problem.
Exclusive OR.
Yeah, a simple logic problem. If input A is different from input B, the answer is true. Otherwise, it's false. If you plot that on a 2D graph, you literally cannot draw a single straight line to separate the true points from the false points.
It's physically impossible. And that failure, that limitation, basically sent AI research into a kind of winter for a while.
It did, until we realized you could get past that limitation by stacking them.
And that gets us to multi-layer feed-forward neural networks. The big idea was to put a hidden layer of these neurons between the input and the output.
And hidden just means they aren't touching the outside world. They're internal processing units.
So what do they actually do?
Geometrically, it's fascinating. If a single neuron can create one straight line, like a ridge, then putting a hidden layer in lets you combine those lines. You can make a V shape, or a bump, or a valley.
Oh, so you could draw more complex shapes. You can draw a circle around the data points in the XOR problem.
You can approximate any continuous function, theoretically. But training them was a nightmare until the invention of backpropagation.
Which is pretty much the engine of all modern deep learning.
It is. It's really just a clever application of the chain rule from calculus. The network makes a guess, you see how wrong it is, and then you propagate that error signal backwards through the network.
You're assigning blame.
You're assigning blame. Output layer, you were this much off. Hidden layer, you contributed to that error, so you need to adjust your weights by this much. It ripples all the way back.
Okay, so while neural nets were getting all this hype for sort of mimicking the brain, another very different approach was being developed that was just pure geometry.
And incredibly elegant. You're talking about support vector machines, or SVMs. The philosophy of an SVM is a little different. It doesn't just want any line that separates the data points. It wants the maximum margin separator.
It wants the widest possible street you can draw between the two neighborhoods of data.
Exactly. And the data points that are right on the edge of that street, on the curb, those are called the support vectors. They're the critical examples that actually define where the boundary is.
But the real magic of SVMs, the thing that makes them so powerful, is how they handle data that isn't linearly separable, the kernel trick.
This is the part that just melts your brain a little. Instead of trying to draw a curvy line to fit the data,
You warp the space that the data lives in.
you project the data into a higher dimension. So imagine you have red dots in a circle with blue dots all around them. You can't separate them with a straight line in 2D.
Right.
But what if you use a kernel function that maps every point's distance from the center to a new third dimension height?
Oh, so all the red dots in the middle would, like, lift up off the table.
They'd form a cone. And now they're floating in 3D space, high above the blue dots still on the table. And suddenly, you can separate them with a linear separator. You just slide a flat sheet of paper between them.
Wow. And when you project that flat sheet back down to 2D, it looks like a circle.
That's the trick. You solve a complex, non-linear problem by just adding a dimension. It's brilliant.
It really is. Now let's shift gears completely. All these methods we've talked about boil the data down into a model, a set of weights or a tree. What if we just didn't? What if we were lazy and just kept all the data?
Then you'd be doing non-parametric learning. And the classic example is K nearest neighbors. It's often called lazy learning for that exact reason. You do zero work up front.
So how does it make a prediction?
When you get a new data point you want to classify, you just look at the whole data set and ask, who are the K closest points to me? Let's say the 5 nearest neighbors.
Okay.
If 4 of them are cats and 1 is a dog, you take a vote. You classify the new point as a cat.
Sounds almost too simple, but I hear it's actually really effective.
It can be, until you run face first into the curse of dimensionality.
The bane of data science.
Our intuition about distance is based on the 3D world we live in. But in machine learning, your data might have 100 features. 1,000 features. That's 1,000-dimensional space.
And geometry gets really, really weird up there.
It completely breaks down in very high-dimensional space. Everything is far away from everything else. The volume of the space grows so exponentially fast that your data becomes incredibly sparse.
I read this incredible fact in the source material that in a 20-dimensional space, almost all the data is closer to the edge of the space than it is to the center.
It's like an orange that is almost entirely peel. There's no middle anymore. So the
Yeah.
whole concept of a nearest neighbor starts to lose its meaning because your nearest neighbor might still be incredibly far away.
So nearest neighbors has its limits. But what about a strategy that actually gets stronger by combining simple models, ensemble learning?
This is the wisdom of the crowd for algorithms. The idea is you take a bunch of weak learners, models that are just a little bit better than random guessing, and you combine their outputs to create one really strong learner.
And the most famous method for this is add a boost.
Right. And what I love about boosting is that it's iterative. It's not just a simple average of opinions.
How does it work?
You start by training one simple model on your data. It will get some things right and some things wrong.
Go.
Then you increase the weight of the examples it got wrong. You basically tell the next model, hey, pay extra attention to these tricky ones that the first guy screwed up.
So you force each new model to specialize on the mistakes of the previous one.
Precisely. You build this committee of specialists, and then at the end, you take a weighted vote from all of them. For the restaurant problem, this method took the accuracy from about 81% all the way up to 93%.
It turns a team of C students into an A-plus superstar.
That's a great way to put it.
So we have this whole toolkit now. Trees, neural nets, SVMs, ensembles. How do they actually perform against each other in the real world? The material points to a classic bake-off. The NIST handwritten digit database.
Yes, the hello world of computer vision. 60,000 images of handwritten digits 0 through 9.
And the results really lay out the pros and cons we've been talking about.
They do. So K nearest neighbors, the lazy one, got a 2.4% error rate. Pretty good, but it's slow.
A convolutional neural net, LINET, designed specifically for images, got that down to 0.9% error.
But in this particular comparison, a highly tuned virtual SVM actually took the prize with just 0.56% error.
But there's a twist, right? We spend all this time geeking out over which algorithm is best.
Is my SVM better than your neural net?
But an analysis in the sources about word sense disambiguation, like figuring out if the word bank means a river bank or a financial bank, it suggests we might be focusing on the wrong thing entirely.
This is the huge data versus algorithm debate. The study showed that if you take a pretty mediocre algorithm, like a simple naive Bayes model, and you feed it 10 million words of data, it will absolutely demolish a much more sophisticated, state-of-the-art algorithm that only gets to see 1 million words.
So quantity has a quality all its own.
It really does. We focus on vertical improvement making the math smarter. But often, the biggest gains come from horizontal improvement, just getting more data. The bottleneck usually isn't the model's complexity, it's the breadth of its experience.
Which explains why the big tech companies with all the data are so far ahead. It's not just better engineers, it's that they have more experiences to feed their machines.
The best algorithm in the world is useless without a good representative dataset.
So we've gone from simple flowcharts to warping the fabric of space-time and landed on the idea that maybe what matters most is just having more examples. It shows learning isn't just one thing, it's a whole collection of strategies for dealing with uncertainty.
And for finding the signal in the noise?
Before we go, I want to leave everyone with a final concept that I think is the perfect capstone to all this. Online learning and the idea of regret.
That's a great place to end. Everything we've discussed so far kind of assumes you train your model once on a big batch of data, but in the real world, the data never stops coming.
It's a constant stream.
Right. Online learning is about updating your model continuously, one prediction at a time. And regret here isn't an emotion.
It's a mathematical term.
It's a metric.
Yeah.
It measures the difference between the total mistakes your learning agent made over its lifetime and the number of mistakes the single best fixed expert would have made in hindsight.
So it's asking, knowing everything I know now at the end of the year, how much better could I have done if I just picked the one best strategy from the start?
Exactly. And the beautiful, mind-blowing thing is we have algorithms that can mathematically guarantee that your average regret will approach zero over time. It means that even in a chaotic, changing world, the agent can promise that in the long run, it won't do significantly worse than the best possible expert, even if it has no idea who that expert is when it starts.
That's a powerful idea. You can't be perfect, but you can guarantee you're learning as efficiently as humanly or mechanically possible.
That's the goal.
Thanks for diving in with us. Hopefully, the next time you see a product recommendation or a self-driving car, you'll see the decision trees and hyperplanes working away behind the scenes. We'll see you on the next deep dive.